Hello everyone, my name is Renan Roque and we are going to discuss about a paper design and 3D print of interconnected porous scaffold for bone regeneration with additive manufacture review. The author of this work is me, Professor PhD Gustavo Franco Barbosa, and Professor PhD Antônio Carlos Guastaldi. So this research was developed in Sao Paulo State University-UNESP, located in Araraquara City, on the Department of Bioprocess and Biomaterials Engineering, and with full support of Chemistry Institute of Sao Paulo State University, that provide all conditions for the analysis and the measurement. We are going to this through consider a presentation content with the initial introduction on the context, and after we are going to discuss how methods, materials used in this research, and the final part, I'm going to explore your useful results and final discussion. Okay, so let's move on. Many applications have emerged as results of the recent advances in the 3D print techniques. For example, 3D print parts have been used for fabrication of aerospace components, prototype and final products in order to manufacture low-cost parts for the industry. Also, the 3D print process has a great potential for different applications in the medical area and tissue engineering, such as 3D bioprinting of tissues and organs, constructions of vascularized organs, manufacturing of customized implants, processes, and models for surgical preparation, among others. Due to these excellent advances faced to the scarcity of organs and tissue available for transportation, the tissue engineer has been considered an ideal type of medical treatment for many health applications along the decades. New tissues regeneration is a branch of biomedical engineering based on the knowledge of biology, chemistry, and physics, becoming a great alternative when conventional pharmaceutical treatments are no longer applicable. Biomedical engineering uses three basic types of tools: cell, scaffolds, and growth factor. Scaffolds are extracellular matrices composed by a complex non-cellular structural network that assists the binding of cells for the tissue formation. And this matrix plays an important role in control of growth and cell differentiation. The scaffold can be 3D printed with different materials as titanium, polymers, and biodegradable ceramics. Also, the 3D bioprinting has been applied to the scaffolds for posterior cellularization and formation of the new tissue and regeneration. In this sense, to relate the relevance of this research according to the Center of Information Technology, Renato Archer, the more complex a solution to fulfill a biological needs, the more natural and more similar the structure of the solution must be. This can be seen in the figure from the use of process in the past, evolving research through the development of biofabrication to bridge the science and technology gap, and even the future of research related to in vivo tissue printing. Biofabrication is the integration of the several disciplines, especially multidisciplinary engineering and life sciences, which interact to develop functional biomaterials and bioprocess, which will be useful and capable of solving major health problems for humans and animals. So, on this way, the proposal of this paper is designing and manufacturing of porous scaffolds being made by 3D print technology from biodegradable thermoplastics, polymers, and calcium phosphate in micrometric scale. So the main objective is to obtain a complex porous 3D structures that present adequate mechanical properties in relation to bonds through a structure interconnectivity between the pores. Related to the porous design of the 3D printed scaffold that simulate the tissues, some properties are essential and needs to be controlled. Surface area and interconnectivity between pores, which are related to the cellular growth, permeability that enables the transportation of nutrients and proliferation of tissues, and mechanical resistance, responsible for ensuring the support and protection of the scaffold, among others. Okay, so let's move on to the materials and the methods. About the biomaterial preparation using the bioprinting and processing, a membrane of polycaprolactone PCl plus amorphous calcium phosphate ACP was prepared in 90-10 ratio. To prepare this mixture, a required amount of PCl is weighted and dissolved in 30 millimeters of chloroform, CHCl3. Once dissolved, the ACP particle size less than 74 micrometers is added, stirred, and the solution is placed in the Petri plate glass. The mixture is allowed to dry at room temperature. This pressure is needed due to the heterogeneity mixture of two phases of this composite material, PCl plus ACP. After that, the obtained membrane, step 1 shows this picture, is used directly into the printer. For using to deplete, this member was rolled up and bent. Step 2, as shown in this picture, to be inserted to the stainless steel syringe for the further heating in the printer. Step 3 is shown in this picture. Architecture of the 3D scaffold. In order to perform the modeling of 3D architecture of the scaffold, the CAD software MasterCAD was used. Thus, two models of scaffold with the same external dimension of 20-28 millimeters were designed, but with different size of the pores, interconnections between pores, and the structural parameters. Model 1 are designed with porous size 300 to 1,700 micrometers with 46% of porosity. Model 2 are designed with porous size 500 micrometers with 40% of porosity. Although two models are designed, only the model number 2 has been 3D printed due to the technical limitation regarding the accuracy of a 3D printer used. So with this, now I'm going to show the result of this research. For this biomaterial, PCl plus ACP, pressure ranges from 100 to 130 psi were tested combined with print head speed ranges from 1 to 5 millimeters per second. Based on this conduct test, pressure of 125 psi and the print speed of 2 millimeters per second have present to be an adequate combination for printed for the model 2. The picture shows the printed sample of Model 2. The parameters that provide the 3D printer of the Model 2 using PCL-ACP biomaterial in the Alivi 2 3D bioprinter were described in this table. As the configuration of the processing parameters depend directly on the type of material, its characteristics of the condition of the system, some preliminary tests of flow of the extruded material were carried out, and in order to determine the properties of this process. The process parameters involve the full functions of the bioprinter, layer height, head speed, system temperature, and extrusion pressure. The load cell and compression rate used were respectively 5 kilonewtons and the 1.3 plus or minus 0.3 millimeters per minute. The software used to conduct the stats was a test script, a MIC version 3.04 from the same manufacturer of the machine used. This picture presents the compression mechanical test performed on scaffolds. During the test, the dimension of each scaffold were measured using the digital caliper in order to feed the software with the information of the area of each sample. With this, all stress and strain curves correspond to these 5 test couples. Typically, this curve will have 2 inflection points, as shown in this graphic. The first inflection point corresponds to the transition between elastic and the plastic strain, which is the maximum of the derivation curve. This kind of behavior has been observed in the literature for porous, PCL, but HA composites. After this initial elastic strain, due to the porous scaffold ability to absorb an elastic energy, there is a result yield with plastic strain. In the last stage of this deformation zone, there is an increase of stress with compressed stress corresponding to the second inflection point, probably due to the collapse of material and clogging of the scaffold pores, leading to a densification of the scaffold. The computational linear static analysis evaluates the displacement, stress, deformation, and reaction force under the stress of the applied load. When this load is applied to the project 3D model, it's deformed, and the result of the load is transmitted in full content. To perform the computer simulation, author-inspired software from author engineer was used. Both models are simulated, and the parameters used on the software can be seen in this table. All this material, as this material PCL plus ACP was newly developed, and the mechanical properties were not defined at the time. Thus, for the software configuration related to the materials properties, it was considered similar properties to biodegradable polymers found in the literature according to these parameters in this table. After all parameters and properties input on the author-inspired software, the computational simulation has been performed. As shown for model 1, we can see the initial stage and the final stage. And model 2, we can see the initial stage and the final stage. It can be observed in simulation for model 1 that the compression load causes a lateral deformation, barrel shape, and proceeds without rupture, characteristics correlated to ductile materials. Among the results obtained by the software, we can be seen in this slide, like some parameters: maximum shear stress, maximum compression stress, and the maximum yield. By comparing the two simulation performances, can be highlighted the difference between the yield values between the models. Model 2 presents a yield rate approximately 3 times higher than Model 1. That is, Model 2 structure allows the displacement between layers easier than Model 1. Regarding the values of compression and shear strip, the values of the Model 2 are approximately 2 times higher than the value of Model 2. This fact can probably be explained by the collapse of the upper layers of Model 2, easier than Model 1. That can cause a pore clogging and the result is scaffold densification. The figure illustrates the difference between the upper layers yield of the two models. This micrography techniques aims to observe the design and scaffold for confirmation of these morphological characteristics. So the first point of evaluation, the print quality is related to design of model. In this picture, it's possible to analyze the structure 0-90 degrees proposed for the structure for the Model 2. Based on this image, is known as architecture ensure the interconnectivity between the pores. In this picture, Again, shows the concept of the repeatability. It can be observed that production process promotes the manufacture of scaffold with similar conformities. According to this image, it's clear and evident that the structure are homogeneous and the uniform condition with the dimension of porous similar structure filament. The second point of the analysis of the B evaluate is of the degree of the adhesion between scaffolding players. Finally, it can be seen the presence of microholes in the surface layers, probably caused by the deposition of a structural filament at high temperature. Thereby, this can be explained by errors of defining of 3D printing parameters when these kinds of scaffold made composite material, PCLA plus ACP, are fabricated. Finally, in this paper, relevant results regarding manufacturing additive technology applied to biomaterial for bone regeneration are presented in connection to the existing literature. Thus, these conclusions are highlighted. The properties observed from mechanical tests, micrographic analysis, and computational simulation show morphological properties compatible with possible application according to the literature. Limitation of this material process principle used by the bioprinting and the complex of the structure model 1, since the structure has connection for smaller than 350 micrometers. Mechanical tests allowed the conclusion that print out scaffold meet the specific required by literature for specific stiffness. The stress strain curves shows that the compressive straight values of the composite biomaterial used are within those found in the literature of the application trabecular bone, being the range 2 to 12 megapascals. The pore size confirmed through the micrographics obtained by CAM are in the tissue engineer application range mentioned in the literature. And due to the trajectory and printing process, the structural interconnectivity between the products is verified. Well, thank you very much. I hope all of you enjoyed the particular issue, which I consider, and that is very important in the tissue engineering area. Thank you for having me and give me this amazing opportunity. Bye. See you.